All right, hi everyone. So my name is Abhishek Jain, and I am a professor at Johns Hopkins University. Okay, so the slides seem to be slightly off. Never mind. So what I want to do today is talk a little bit about some research that we have been doing at Johns Hopkins and colleagues at different universities on sort of new cryptographic tools that we think will be useful for blockchains. In other words, what I want to talk about is some tools that have new properties that are inspired by their potential applications to blockchains. And the talk will be mainly high level. I will just introduce the new ideas. And if you're interested in details, you can, of course, ask me about those things later. OK, so I'll talk about a few different things just to give you a taste of these ideas. And the first topic that I want to talk about is related to this primitive called zero-knowledge snarks, ZK snarks. This is something that you may or may not have heard about. It is something that has lots of applications for various blockchains. I'll talk about some of these applications in a moment. But what I want to talk about is how to improve the scalability of ZK snarks. And let me start by just explaining what are ZK snarks to begin with, if you haven't heard of them. So ZK snarks are short for zero-knowledge, succinct, non-interactive arguments. So it may sound like a mouthful. So there are lots of properties associated with this primitive which make them really desirable. So first of all, ZK snarks are a form of proof system. Okay, so what do I mean? So we have two parties. There is a prover who wants to prove a statement to a verifier. And the way he wants to convince the verifier is by sending him a single message which attests that the statement is indeed true. Now, he may have some public input associated with proving that the statement is true, and he may also have some private input or a witness, which could be secret, and he wants to keep it secret from the verifier. And we want the following properties. So first of all, we want that the proof should be very small. So if takes the prover a long time to actually compute the proof, we want that the verifier should be able to receive a very short proof, and which is very fast to verify. So this is the succinctness property. And you can imagine that this is very useful blockchains when, for example, we want to communicate these proofs over blockchains. They save on bandwidth. Validators can verify these proofs very quickly. So that's why they are very useful. The second property is the zero-knowledge property. And this property essentially says that the secret inputs that the prover uses in proving the statement. Yeah. Hello? Okay. Maybe I was too loud earlier, or? Okay. All right. So the second property is zero-knowledge, which essentially says that the secret input that the prover uses in proving the statement should actually remain hidden from the verifier. So the verifier has no idea about the secrets used in the proof. The only thing that the verifier learns is that the statement is true. Okay, so now let me explain why do we care about these objects. So first of all, these objects are useful for privacy reasons because of the zero-knowledge property. So you can use them to build anonymous credentials, which in turn can be used for blockchains where you care about privacy. So in fact, these are heavily used in some blockchains like Zcash and some other ones as well. They're also useful for rollups. So essentially for improving scalability of blockchains, because instead of posting every transaction on the blockchain, you can actually keep them outside and then only keep a short digest on the blockchain, which verifies that all of the large bunch of transactions were actually correct, and so on and so forth. Okay, so these objects first introduced in academia and in cryptography. They have now undergone a lot of research over the last 10 years or so since their introduction. Part of it has been because of the applications to blockchain. And the research has, in fact, both been academic and from industry. And really, there are like tons and tons of papers out there on ZK snarks. While they started being very theoretical tools, now they have evolved to very, very practical solutions. We can, in fact, have proofs which are constant size, so it doesn't matter how big of statements you're proving, the proofs will be small, the verification time will be very fast, and in many cases, we have also evolved to improving the prover time significantly. Nevertheless, despite all of this amazing progress, the main bottleneck that we care about in the current state of the art for zk-SNARKs is the prover time. How long does it take for the prover to compute a proof for some complex statement? So essentially, the main challenge that we currently want to address in the research on zk-SNARKs is how can, let's say, a user with a commodity laptop, commodity hardware, compute zk-SNARKs for complicated statements, very large statements that involve a lot of constraints. So what I mean by a lot of constraints is just think of the statement that I want to prove represented as some circuit, and I'm thinking about the number of gates in the circuit, or you can think of equivalent forms of representation as well. So this is the question. And of course, I can do some standard things. I could, for example, use an AWS server to compute the proof for me. If I want even faster performance, I could maybe employ a cluster with lots of parallelism, and then use their services to compute the proof. So these things do work to an extent, but there's one big problem with these approaches. I always have to disclose my private witness to these servers to actually compute the proof for me. So while doing so, at the some gain in efficiency, I lose privacy completely. Okay, so we want to basically come up with a way of computing zk-SNARKs very quickly, allow clients with very low resources to actually obtain zk-SNARK proofs computed very quickly while retaining privacy. That's essentially the goal. And this is sort of our vision. The vision is that a client with very low resources can somehow encode the statement and maybe the witness used for computing the proof to a lot of nodes on the internet. Okay? And I don't care what capability the nodes have. They could themselves be computers with very low resources. They could be some servers. It doesn't matter. From my perspective, they could all be laptops. Okay? And that should be sufficient. And what we want is that this collection of nodes should then be able to come together, compute a proof that the prover actually wanted. And I want the following properties. So first, I want that the proof should be generated very quickly, much, much faster than it would take for the client to actually compute it itself. Right? And in fact, I want that the more machines that participate in this computation, the faster the proof generation should be. Now this, of course, on its own may not sound very interesting. If I am employing a whole bunch of nodes on the internet to compute the proof for me, sure, maybe I can compute it much faster. But I also want that actually if I employ a lot of nodes, my cost should not increase. So in some sense, whether I employ 50 nodes or 100 nodes or 150 nodes, my financial cost should remain roughly the same. Okay, so now this, again, may sound a bit crazy, but I'll explain in a moment why we can hope to achieve this. And the final property, which is what I alluded to earlier, is that I still want privacy. So in other words, what I want is that even if a subset of the nodes that are participating in the proof computation are corrupted by, let's say, one adversarial entity, still zero knowledge property should. Okay. So this is what we built. This is very, very recent work. We finished writing the paper last week, so this is really fresh. So we built what we call zk-SaaS, basically a framework for outsourcing computation of zk-SNARKs. So this is not a completely generic system yet. It currently supports certain kinds of SNARKs. So basically the idea is that if you have zk-SNARKs that follow certain structure, then we can actually show how to compute them very quickly using our system. And just some preliminary numbers just to give an idea that it is effective. So just by using a few nodes, like 64 machines with very low capabilities, we could actually speed up the computation by roughly 14x. The corruption assumption was fairly standard, 1/4, but you can increase it to 1/2. That's fine. And the numbers that I write here are for perhaps the most popular zk-SNARK, which is Groth 16, because it has the shortest proofs till date. Okay, but the system supports some other popular zk-SNARKs as well. Okay. So the main tool that we use is something that we have known in cryptography for 3 or 4 decades. But with a twist. So the main tool is secure multi-party computation, what is also referred to as MPC. And this is an amazing object with properties that sound paradoxical. But basically, the idea is that it allows a bunch of parties who each of them have some different and private input. So in this picture, you can see there are 6 parties that have inputs x1 to x6. They want to compute some function, let's say some circuit C, on their inputs together. And we want the property that at the end of some protocol that they run, they should be able to learn the output of this function on their inputs, but they learn nothing else about each other's inputs. Okay, so very strong privacy guarantee. So of course, if I use a tool like this to compute a zk-SNARK, I can hope to preserve the zero knowledge property of the zk-SNARK, because even if some of the machines in the MPC are corrupt, that's okay. So that's fine. But the main novelty in our design is actually the use of a new form of MPC, which for simplicity, I'm just referring to as a scalable MPC. So what do I mean? So normally when we build secure multi-party computation protocols in cryptography, they have this annoying aspect that every party involved in the computation usually has to perform at least as much work as the original computation that you wanted. So if I want to compute a circuit C, every party involved in MPC must perform work as much as the size of the circuit C. And this means that MPC in general is not really good for outsourcing, because what speed up do I get? If everybody is performing as much work as the original computation size, I don't really get any speed up. So what we are actually building is a form of MPC for this particular functionality of zk-SNARKs, or a particular class of zk-SNARKs, where you actually get division of work. So the total work gets divided amongst all the nodes that are participating, and therefore, the more the nodes that participate in the computation, the faster your computation is going to be. So that's essentially the main idea. Not going to explain how we build this MPC, but just this is the novel property that we achieve. Okay. So let me use this opportunity to actually plant a flag for MPC. So MPC, I believe, has a lot of potential for blockchains, and perhaps one of the potential applications for which it could be very, very useful in the future is private smart contracts. So what do I mean by private smart contracts? Essentially, smart contracts where the inputs that are going to the smart contract are private. They need to stay private. That's my requirement, right? So they involve like some secret information of the parties that they don't want to disclose to everyone on the internet. And currently, there are only very limited solutions for private smart contracts, and there is essentially no solution for the scenario where the inputs are coming from multiple different parties, and they have no incentive to trust each other. So in this case, in theory, I could hope to use an MPC protocol to implement the logic of a smart contract, essentially by just secret sharing the inputs of the parties amongst, let's say, a bunch of miners, and then the miners run the MPC protocol amongst each other to implement the logic of the smart contract. So that's a theoretical idea, but there are many obstacles to actually realizing this idea so that it can actually be used in blockchains. So I'll just give you a glimpse of a couple of challenges in this direction. So one major challenge is that when we design MPC protocols in cryptography, typically they are very intensive, and moreover, the amount of interaction that is involved in the MPC protocol, it scales with the complexity of the computation that you want. Okay. So if you want to do a computation, let's say, which is represented by a circuit of depth 1,000, then usually your protocol may involve actually 1,000 rounds of interaction, which doesn't quite make sense. You will now need all the parties involved in the computation to stay online for that entire duration. And in fact, this is why we could not have employed many classical BFT protocols to do consensus when we started building blockchains, because classical protocols were not really suited for this kind of setting. At least this was one of the reasons, if not all the reasons. And so essentially, one new idea that we have explored very recently, this is something that was published last year at the annual crypto conference. We basically started looking at new design of MPC protocols where actually the parties don't need to stay static throughout the computation. They can actually keep on changing. So even if I want to do a computation that spans multiple rounds of interaction, every round the parties can change. If you are familiar with a blockchain like Algorand, this is sort of a similar style of property that we investigated in the context of MPC. And then there's yet another issue that arises when using MPC protocols in many blockchains. So many blockchains, they involve, for example, stakes, where parties have stakes, or they may have some reputation scores, right? And this is not really consistent with the MPC protocols, because there, all parties are usually treated equally. So now if I want to handle a setting where parties are asymmetric, then sort of the only natural approach would be to just imagine, let's say, a party that has, let's say, 1,000 stake as 1,000 virtual parties. And then, just use a standard MPC protocol. But this is not really ideal, because now a party with 1,000 weight would have to do 1,000 times the work of, a regular party. And this is not really scalable. So again, we have been doing some work to actually avoid this kind of overhead, and we have some new solutions in this setting. Okay, so let me just use the last maybe 2 or 3 minutes to talk about a completely new topic, or completely different topic, regulatory compliance in blockchains. So let me add some disclaimers. I'm only going to talk about this topic from a cryptographer's perspective. I'm not a policymaker, lawmaker, etc. So I'm not going to discuss what kind of regulation compliance should we do should we support in blockchains and so on. I only care about the following: that if we all agree that we should have regulation compliance in blockchains, then we should be able to do so while retaining the core appealing features of blockchains. So in particular, any regulatory compliance that we support should not really compromise the features like decentralization and privacy, etc. That's sort of the premise that I want to start with. So for this reason, the following kind of very simplistic solutions are not really desirable. So I don't want solutions where we just have some authority that has a master key, and that can see everything that is going on in the blockchain, can de-anonymize anyone, can undo things and whatever, right? So we don't want those kind of solutions for very obvious reasons, because you have to always trust that that authority is acting honestly and not going to do any overreach. Okay. So let me actually draw a parallel to a different setting which has similar kind of tension. So in the very different setting of secure messaging systems, people are currently concerned about the following setting. So on the one hand, because many messaging systems like WhatsApp, Signal, etc., they use end-to-end encryption, lawmakers are concerned about the fact that they cannot see if people are doing, if criminals are communicating using these platforms, or whether they are uploading illegal content like child sexual abuse material or short CSAM on these platforms. So they want the ability to actually do some regulation or content moderation on these platforms. So they are advocating for backdoors on these systems. But of course, privacy advocates do not want to allow for backdoors, and tech companies, they don't want to give backdoors or actually have backdoors in the first place, because that would just completely destroy the transparency of the system, right? So they don't want. So this is like this conflict, and the question is whether these are just completely in conflict, or whether we can actually somehow find a middle ground. That's the question that I'm interested in. And my claim is that actually there is a middle ground, a very meaningful middle ground that can be achieved by using a new form of cryptography. So what I call cryptography without master secrets. Okay? So typically in cryptography, if you, let's say, think about an encryption scheme, if I have the decryption key, I can decrypt all ciphertexts corresponding to that key, right? And this is what allows the owner of the decryption key to have the key escrow power. And we don't want this. So what I'm proposing is actually a form of cryptography where there are no omnipotent keys. Instead, when you design the system, at the system setup time, you actually bake in or lock in a policy that basically ties the hand of the system authority. So think of a policy which basically says, okay, you can only check if an encrypted message contains CSAM or not, but you cannot check anything else. Okay? So I can prescribe this as a form of policy, and then I can lock it into the system setup. And now, later on, the authority basically cannot do anything. Even, in other words, even the master key of the system already has limited functionality. Okay, so this is kind of against the usual idea that we pursue in cryptography, where we want to add functionality. Here, I'm actually removing functionality from the system by design, and this is what is going to give us the security that we want. And basically, if we have this feature, then we don't need to trust authorities, essentially, because we know that even given the master key, they cannot really do any overreach. So we have some preliminary work on this topic. Last year, we published a paper where we established the theoretical foundations of the system, and then more recently, we built a practical system, at least in the context of secure messaging. What remains to be done is actually applying these ideas for regulatory compliance in blockchains, but I think there's a lot of promise. So I think with that, I'll conclude.
Amazing. Thank you so much for this conversation. Next up, we have...
Oh, thank you very much. Hello. Hello, everybody. Hi. Out of interest, who thinks, hands up if you think you understand the Stellar Consensus Protocol a little bit. Don't be shy. Okay, and hands up if you don't. Your vote matters because it'll change how I present the talk. So pretty much, well, nod me along if I go too slowly through the SCP parts. I also have a prop, a shirt, which I will come to in a minute. So some of this has already been covered by David. There's various systems, proof of work, proof of stake, proof of authority, and if I push this red button, will it end the conference or send out a laser? Laser, cool, thank you. Aha, cool. So Stellar isn't proof of work, so it has low energy consumption. It's not proof of stake, so the rich don't rule the world, at least not in the blockchain sense. It has proof of authority, but also Stellar's permissionless. So you have this notion of authority, but anyone can join, which sounds a little paradoxical, but it works magically. Hands up if you're with me so far, please. Ola, are you with me so far? You can put your hand up. Thank you, great. But it's got this quorum system, which if you're used to Ethereum or Bitcoin, looks like it came from another planet. So it could be better understood. So let's just spend the first third of the talk just trying to understand this better. So I'm a mathematician, so here's a definition. Oh, by the way, with reference to the question by the gentleman in the green top, who very foolishly has wandered out of the talk before I came to speak, I am based in Europe. No. So this is a semi-topology, which is a set of points. Think of these as participants. You can all be points if you want. You're a point. Congratulations. And a set of open sets, which are like quorums. Okay, so points have quorums, and a union of quorums is a quorum. Yeah. So if you studied topology in uni, this is the definition of a topology, except that the intersection of two quorums need not be a quorum. For example, if you're all points and the quorums are just a simple majority, the intersection of two simple majorities might be a single participant. So semi-topologies are not topologies, but they have a definite topological feel. Yes, of course, certainly. Power set. Power set. The set of subsets of. Sorry, so this is just a fancy way of saying that an open set, a quorum, is just a set of participants. POW is just a fancy mathematician's way of saying that. So don't sweat the notation, I won't use it again. Yeah, exactly, mathematician, thank you. So here's a worked example. So I'll just modify slightly from what's on the slides. Before I went here, I have quorums regarding how I dress. My quorums are, well, there are 4 participants: myself, my wife, my son, and my mother-in-law. Right? You may recognize this setup. And the quorums are, I have 2 quorums. This is literally true. So there's me and my wife, and me, my son, and my mother-in-law. And when I'm deciding what to wear, in order to finalize and agree on a decision, I need at least the agreement either of my wife or of my son and mother-in-law. So I'll just modify this slightly. Here's the shirt, right? So I had the question, what should I wear to give this talk? Should I wear a shirt or not? So I asked my wife, and she said, you must wear a shirt. But I wasn't sure, so I tried my other quorum. Son and mother-in-law, wear a shirt, Jamie. So I bought the shirt. So why am I not wearing it now? This is not on the slides. It's because I changed my quorums. When I turned up, I looked around to see what everyone else was doing. You are now my quorum. Most of you are not wearing shirts. So I thought, to fit in, I should dress down. Okay? And it's not universal, right? There are some people in shirts here, but I read the environment. So this is a quorum system in action. I'm wearing a T-shirt because I changed my quorums. Now, Stella's consensus algorithm essentially contains an engine for computing quorums. That's what it does. Every 5 seconds, it reaches a new quorum state on how to proceed. That's what it's doing. So here's an arbitrary semi-topology. Here are the quorums. The participants are collectively illustrated by the white spaces. So here's an arbitrary semi-topology. There's no reason to expect an arbitrary semi-topology to reach consensus. The way I think of it is, if I got a bunch of coins and threw them on a table, the system reaching consensus might be all the coins end up standing on their edges. It would be weird. If we saw this behavior, we'd say, hang on. There must be something underneath the table. What's going on, right? And yet Stella works. So can we use maths to understand what's going on? So very briefly, again, those of you who remember, who studied topology, might recall the notion, who remembers the notion of a Hausdorff space? Abhishek, you must know what. You don't know what a Hausdorff space is? Okay, I'm not picking on you. It's pretty much the first thing you learn when you study topology. A Hausdorff space is such that for any 2 points, any 2 participants, each of them has its own quorum and they do not intersect. And this is that written in math notation. By the way, I spent a day trawling the LaTeX symbol list to find the perfect symbol. I'm very proud. This is my contribution to topology, right? That symbol there. That I thought of that. I found it. So if, like me, you're a mathematician and you studied topology in uni, then this is your bread and butter. And now we're going to invert it. We're going to call 2 points intertwined when they don't have disjoint quorums. All of their quorums intersect. Here's a picture. Now, I mean, you can check. Every single one of these, it's a Venn diagram, every single neighborhood intersects with every other one. This is a highly intertwined system. And if we think of this as quorums, it's impossible for 2 quorums, each in agreement within themselves, to disagree between each other, because they all have non-empty intersection. And that, yes? I'm sorry, I can't hear you. Say again. Oh, so if you take this property here, which is a Hausdorff property, and apply a negation here, then you get, this is technically, it's called the De Morgan dual. So there's a logical process by which you can take one predicate and produce its negation. Mathematician. But I mean, this is a well-known procedure. So let's just try it on this example, which, by the way, This took me a day. So are 1 and 2 intertwined? So they're intertwined when they're not Hausdorff, when they're intertwined. Absolutely, you're fast, well done. I agree. So let's just try it on, here's one quorum of 1, and 2 has a quorum 0, 2, 4, and they intersect, in fact, on 2. Fine. Are 3 and 1 intertwined? Hands up if you think 3 and 1 are intertwined. Okay? Hands up if you think they're not intertwined. They're right, I'm afraid. And so the counterexample is 3 is a singleton, and 1 and 2 are a neighborhood. So 3 is a guy who is perfectly happy putting on whatever he or she wants in the morning, doesn't need anyone else's agreement. They just do their own thing. Yeah, exactly. So basically, -1, 1, 2, and 0, they're an intertwined group. So if they were going out clubbing in the evening, they'd always go out together, right? Because they have to agree on the club, because they're intertwined. Whereas 3 and 4 might be doing their own thing. Or they might join in, it depends, but they don't have to go with the rest of the group. So the answer's here. Where I had these slides proofread, and the gentleman who proofread it said, I love the slides for one thing. If you've made a mistake, part of the text is printed upside down. Anyway, so, so once you've set this up, then the notion of consensus becomes identified with the notion of topological continuity. Now, reading this audience, you might not have heard of topological continuity, but you'll have an idea of a continuous function being smooth, right? So this powerfully generalizes in topology, and I'm not sure whether I should go through this, but it basically the observation I made before, that if 2 points are intertwined, so all of their quorums intersect, they cannot disagree. If the quorums have agreement within themselves, then any points in these quorums have to agree, because the quorums have an intersection. So if the 2 quorums agree with internally and they have an intersection, then each quorum has to agree with something in the intersection, and therefore you have continuity across the quorum. Hands up if that made sense, just reassure me. Hands up if it didn't make sense. Okay, cool. So you're going to be the intersection of 2 quorums, sir. Okay, so because you're going to be in a quorum with that gentleman there, and you are going to be in a quorum with David over there, okay? But you don't know David, okay? Now, please could you pick a colour? Pick a colour. Perfect, thank you. Nice colour, by the way. I had you pegged for green, but blue is good. So now, you have to pick blue, because if you're going to be in consensus, you only have 1 quorum, and this guy in the set, what's your name, please, sir? Joseph has chosen blue, so you have to pick blue. I mean, you can argue with Joseph, but eventually you have to agree on blue. Does that make sense? You're looking completely blank. Okay. Yeah, I am talking to you. But that's fine. You can pick green, but now you're not in a quorum with Joseph. So the 2 of you cannot make progress. Right, which is fine. If you want to block locally, that's fine. But to make progress, the 2 of you have to agree on the colour. Thank you, that's good of you. Right? David, do you want to pick a colour? There you are. So now you see David, what's your name, please? Jacek, as in Yitzhak. Okay, Jacek, interesting. So Jacek and David have never, well, for the purposes of this, they've never met, they haven't communicated, but because they share, their quorums have an intersection, I know that you 2 will agree. That's continuity. I'm going to move on because I'll run out of time. But this corresponds to Stella's safety property. Intertwined points never disagree. This means no forking. Right? That's what it boils down to. So Stella has this property that it works. This is the maths. The mathematical statement and proof. There's another important property. that I'm going to call S a topen. This is the most technical slide in the talk. I'll call S a topen when it's an open set, that means a quorum, and it consists of points that are all intertwined with one another. So S must agree by the intersection property, and it can progress because it's a quorum. Being a quorum means you can make progress. So there is a theorem, which is not hard to prove, that an arbitrary semitopology, you generate any semitopology, you can be as nuts as you want, it will naturally partition itself into topens. Semitopologies naturally form into communities of agreement. That's really good news. If you're trying to run a blockchain, it means that no matter how the participants choose their quorums, they will self-organize, this is mathematically guaranteed, into camps, into groups. Preferably at the one, right? Preferably there'll be just one token. But if you think about other blockchains, they have a similar property, although it's not labeled as such. For example, Ethereum has mainnet and testnet. Right? These are, if you like, two communities. And in fact, there, it would be a bug if testnet influenced mainnet directly and vice versa. So don't be worried about multiple tokens. This is just an abstract mathematical statement that a semitopological world must form into what we actually see in real life. There are communities that believe that people should wear shirts when they present in a conference, and a community that doesn't, and that's fine. So, Theorem 1 provides a high-level account of consensus. You let participants choose freely whom to trust, derive a semi-topological notion of quorum, which these witness functions are the slices. This is a part of the research that I don't have time for. It's another talk. And then you just compute continuous value assignments. So at a very, very high level, that's an overview of how stellar consensus works. But it's not just for stellar. This resembles real life. If you think about it. I like to think of, like, I like dark, heavy beers, and my wife likes light beers, like Heineken, Corona. And the world kind of, you get people who agree they like Belgian beers, or they like whiskey, or they like light beers. So these communities form all the time, and they reinforce one another. They talk to each other, and they come to agreement. And there's no incentive. There's no payment for that. That's just how societies work. Any questions before I move on to the last slide? How's my pacing? Is my pacing okay? A bit late to ask now. Yeah? Cool, thank you. So let's just see where we're at. Yeah, okay. So, I'll very briefly touch on this. The fact that, I covered this briefly before, of course, the fact that semi-topologies can partition into more than one token is a feature, not a bug. And another reason is it's a source of Stellar's Sybil resistance. An attacker can rock up to the Stellar network and create a million nodes. But until existing participants start trusting them, all the attacker will succeed in doing is creating a separate token which just does its own thing, but is not connected to what we socially consider the main network. So I've discussed Stellar with people, and sometimes there's this knee-jerk reaction, no, people can create their own tokens, that's a good thing. And separate token is something that the main net doesn't trust, and that's a feature, not a bug. Okay. So, open questions and future world. The original goal of this research was to attain a simple mathematical understanding of the principles of Stellar. This talk presents a part of this analysis. So it would be nice if we could develop better algorithms, especially for leader elections. This is a topic of active research. Right? So once we have this notion of semi-topology, can we basically design algorithms on semi-topologies which we can then turn into code? That would be neat. Can we use the maths to develop what I might call leading indicators for network instability? Could we prove results that say if a semi-topology has certain properties, then it's safe? And then we use Stellar Beat to monitor the system. And it's not necessarily the case that if these conditions are broken, then the system would necessarily immediately break, but it might be a warning signal for people to take a look at what's going on. And then the fourth thing is the Stellar quorum model is a bit different, and my current thinking is that it's closely related to social choice. I think David used the word voting in his talk. So voting, oh, I'm out of time. Okay, I'll just wrap up. So social choice is a mathematical field of studying how to vote. If you have a community and they all have different opinions, how can we produce a single preference, a single action that somehow represents a community? And it seems to me this is what Stellar is really doing. And this could be generalized, for example, to governance of DAOs. Many DAOs use a governance token mechanism based essentially on incentives and tokenomics and stuff. It doesn't have to be that way. It's certainly not how societies organize themselves. Again, David, you were touching on similar points. So perhaps what we really have here is a notion of permissionless social choice, which, if so, would be a new field and a very interesting one. And this too is current research. Thank you all very much.